Hello children, welcome back to the channel. Today, as promised in my previous video, we will be taking up a couple of problems, as I said, supplementary problems. You can consider it as problem or as a theory also. What happens is that let's consider the case of a solid cylinder rolling down an inclined plane. Now what do you mean by rolling? That the object is moving about an axis which is the point of contact with the surface it's rolling on. For example, the wheel of a car, when it moves, it rolls over the road surface. So, for rolling without any slipping, the important point is that when the point of the object that is rolling, the point in contact with the surface over which it is rolling will be stationary. So, when this solid cylinder rotates or rolls over it, over the surface, this point of contact will momentarily be at rest. Then it moves a bit further, next point comes into contact, that point will be at rest, and so on and so forth, so that down the incline the object is not having any slipping over the surface. Now this surface is not smooth, but it is supposed to be rough surface, that is, it will offer certain amount of friction. Okay, so when an object, for example the cylinder or a disc, rolls over a surface, the surface must, number one, provide certain amount of friction, and number two is that rolling without slipping means the object will be moving in a kind of a rotation. However, the point in contact with the surface will always be stationary. So when it rolls, it will roll about this particular axis, and now as the object rolls, it will gather certain amount of linear velocity. The velocity we can consider to be the same as the velocity of the center of mass of the object. Okay. Now, to find the acceleration of the body or the dynamics of the system, what we need to understand first is that what are the different forces that are acting on it. Now, what are the different forces that are acting on it? Number one will be, if this is the center, that will also be the center of mass of the cylinder. So, the weight of the cylinder will be acting vertically downwards, right? This will be, say, mg. Then there will be a normal reaction perpendicular to the surface. Let's call this n. And a third force will be there, which is the force of friction, which will be trying to oppose any slipping between the object that is rolling and the surface in contact. And this is the force that is causing the object to move in a rolling motion without any slipping. So third force is the force of friction, which is acting along the surface opposite to the direction of motion of the center of mass, which will be down along the inclined plane. Let's say the inclination of the plane is given by theta. Okay. So what we will do is that for our convenience we will resolve the weight into two components, one perpendicular to the surface and one along the surface. Okay, this component will be mg cos theta, and this component will be mg sin theta. Okay, so as we have discussed in the laws of motion, applying Newton's law to the direction perpendicular to the plane, the normal reaction must be balanced by, or must balance mg cos theta. Otherwise, what will happen? The object will sink into the surface. Since it is not sinking into the surface, means that the normal reaction is balancing the downward force along the incline, that is mg cos theta. And also, since the center of mass of the object is moving, and since there is a net unbalanced force down the incline, so there will be an acceleration. Let's call this A. In that case, net downward force must be equal to mass of the cylinder multiplied by acceleration that is produced. And what is the net unbalanced force F? It is simply downward force mg sin theta minus the force of friction, as we discussed in the previous chapter of laws of motion. So number one and number two, these are our first two equations. Now let us consider that since it's a rigid body, we can always consider its whole mass to be concentrated at the center of mass, which in this case is the center of the body. So if the mass is concentrated at here and force of friction is acting at the circumference of it, right? So this force of friction is responsible for a torque. So this is the force of friction and this is at a 90-degree angle with the radius vector. Let's say radius of the cylinder be r. In that case, the torque that will be produced by the friction will be simply tau equals to F into r, since radius vector and the force are at 90 degrees to each other. But for a given rigid body, we know that tau can also be given by, if I is the moment of inertia and alpha is the angular acceleration, then I alpha is equal to tau. We have already found in my previous videos. If you haven't seen those videos, then the link to my playlist on rotational motion, system of particles and rotational motion, as well as my other playlists are given in the description. You can always refer to them. So since the object is moving like this and there is an angular acceleration that will happen, so I alpha will be equal to Fr, which will give us force of friction. From this equation, we can say force of friction can be given as F equal to I alpha by R. Fine. Which must be equal to I. Now we already know that for rotational motion, R into alpha will give us linear acceleration A. Or we can say that alpha can be given by A by R. So if you substitute this will be A by R square. We say since A is equal to R alpha. Okay. So if we substitute this value of force of friction into equation number 2, so equation number 2 will give us MA equal to mg sine theta minus IA by R square. Let's take the terms with acceleration, linear acceleration to the left hand side. So we have m plus I by R square into A must be equal to mg sine theta. Okay. If we take m common, we will have m into 1 plus I by R square into A is equal to mg sine theta. M's will cancel. Hence, we are left with the equation that linear acceleration of the body, of the center of mass of the body down the incline, will be given by g sine theta divided by, there will be an m here, 1 plus I by m R squared. Okay, till now? Fine. Now, this is one of our results, that linear acceleration is this. Now we already know that for a solid cylinder, moment of inertia I about its axis is given by half m R squared. Right? Which will mean that this equation, this particular equation, if we substitute that value, we get g sine theta divided by 1 plus half m R squared by m R squared. M R squared will cancel, so this will be 3 by 2 in the denominator, so it will be 2 by 3 g sine theta. Linear acceleration of the solid cylinder will be 2 by 3 g sine theta. Now, here we need to notice one important thing is that this linear acceleration is independent of the body. Sorry, it's independent not of the body, type of the body, but the mass of the body, of course, yes. It is independent of the radius of the body also. Right, if we have a small solid cylinder or a large solid cylinder, a light solid cylinder or a massive solid cylinder, things will not change. The linear acceleration will be this only for any type of solid cylinder that is rolling down the surface, as long as F is the same. Now we need to note from here is that A equal to 2 by 3 g sine theta. So what it means is that the linear acceleration depends only on this term theta. That is to say the inclination of the plane. Okay, so for solid cylinder, what we have found, A equals to 2 by 3 g sine theta. Now we have found an expression for acceleration for solid cylinder, right? So if we substitute this value in equation number 2 for A, therefore equation number 2 will give us 2 by 3 m g sine theta must be equal to mg sine theta minus f. This will give us f must be equal to 1 by 3 mg sine theta. So the force of friction must be equal to mg sine theta. Now what is the significance of this particular result, F equals to this? See, we already have seen that the force of friction is the one that is holding the object or the solid sphere or sorry, the cylinder from slipping. So for no slipping, that is to say for pure rolling motion, or in other words for the object or for the solid cylinder not to be slipping down, the force of friction must be equal to this, or in other words greater than this, which means that since we know F equals to friction is given by mu s into n, right? Since mu equal to F by n, coefficient of static friction is force of friction divided by normal reaction. So this equation will give us that this must be equal to 1/3 mg sine theta, or if we substitute n from here, we get mu s mg cos theta must be equal to 1/3 mg sine theta. That is to say mu s must be 1/3 tan theta, right? So for the object not to slip, the coefficient of friction mu s must be greater than or equal to 1/3 tan theta, the inclination. If theta is such that 1/3 tan theta is greater than mu s, in that case the object will not be able to continue its pure rolling motion. It will have to slide down the object, as the coefficient of static friction, that is to say limiting static friction, or in other words the frictional force will not be sufficient enough to keep the object in pure rolling motion. Now as the object is rolling down, it will have certain amount of kinetic energy because of its motion, right? So what will be the kinetic energy of rolling of the object, of the cylinder? So kinetic energy must be the sum total of kinetic energy of the translational motion of the center of mass, because the center of mass or the object is moving linearly downwards, and also it is having a rotational motion, right? So this plus kinetic energy of rotation, but that will be of the center of mass, because center of mass will also be rotating about it. So that entire motion of the body, rotational motion, can be considered to be the same as the rotational motion of the center of mass. Now this must be equal to half m into v cm, center of mass is velocity squared at any given point, plus half I omega squared, where I is the moment of inertia of the object about this center, and also omega is the angular velocity at that particular moment when VCM is the linear velocity of the center of mass, which must be equal to half mvcm squared plus half I. Omega is, see, r omega equal to v, so v omega will be v by r, that is vcm by r whole square. Right. Therefore, total kinetic energy of rotation or rolling will be half m vcm squared. If we take this common, what we are left with? First term will be 1, and the second term will be, there is I here and there is r square, right? I by r square, and we have taken m, so m will come here, right? Now we already know that I can also be given by m into k square, where k is the radius of gyration. Now this k and this k are different, so we take kinetic ke here, that will be clearer. So k is the radius of gyration. So if we substitute I with mk square, then we get, this will be m into k square. That is to say, total kinetic energy will be of rotation rolling will be half m into vcm squared 1 plus k squared by r squared. Okay, now let's take up the case of a point mass m tied to a solid cylinder which is free to rotate about its axis through a massless inextensible string. So there is a massless inextensible string wound around a solid cylinder which is free to rotate about its axis. The mass of the cylinder, let's say it's m, capital M, or whatever it is, and it has a radius of say r. Okay, so if you look at this, what we want to do, we want to find the dynamics of the system, that is the tension in the string, the linear acceleration of the mass, and also the angular acceleration of the cylinder as a whole. Now, if you look at it from a side-on view, what we will see is that it's look like a solid disc, and the mass will be hanging from here. This will be the mass, and this will be the radius of the cylinder, right? So, looking at it from the side-on view, we can find what are the different forces acting on it. First of all, there will be, of course, the weight of the object, that is mg. The point mass that is hanging on it. Then there will be an upward force of tension in the string, as we know. So these are the two forces acting on it. So if the object has a downward acceleration, the point mass has a downward acceleration of a, then Newton's second law will give us that point mass into a will be equal to mg minus the force of tension. Okay. Now, if you consider this case, since this is the radius and this is the tension, they are at 90 degrees to each other, right? Now, this tension is the cause of rolling or rotation of the cylinder about its axis. So, this will produce the necessary torque in the cylinder. So, the torque in the cylinder will be T into R, right? But by definition, if I is the moment of inertia of the cylinder, then I into alpha will be equal to this, right? Which means the tension will be I alpha into R, which is equal to I A into divided by R square, since alpha equal to A by R. For rotational motion, pre-rotational motion, the linear acceleration will be angular acceleration multiplied by the radius from circular motion. If we substitute this value of t in this equation, equation number 1, therefore equation number 1 will give us m into a equal to mg minus ia by r squared. This will give us a minus ia by m r squared must be equal to g. What we have done, we have divided both sides by m and then transferred this to the left hand side. That is to say, if I take a common and this will be plus, right? Yeah. So we get g divided by 1 plus I by m r squared. That is to say, linear acceleration a of the mass, downward acceleration, will be given by acceleration due to gravity divided by 1 plus I by m r squared. Now, this expression clearly tells you, since the denominator is 1 plus a non-zero term, means that the acceleration a must be clearly less than acceleration due to gravity. And this loss of acceleration is due to the moment of inertia that is causing the object to resist any change in its motion, thereby rotational motion, okay, for a cylinder. Now, this means that since alpha equal to a by r, therefore alpha must be equal to g by r into 1 plus I by m r squared. Fine. That is to say, angular acceleration alpha is given by g by r divided by 1 plus I by m r squared. So, this expression t equal to ia by r square, equation number 2, now can give us the expression for tension in the string. T will be equal to I, instead of a, we are going to substitute the value, right? So I by r square is there, and then a will be substituted by this. So it will be g by 1 plus I by m r squared. Fine. So this will be equal to I by r squared g by, if I take I by m r squared common from here, we are left with m r squared by I plus 1. We have taken I by m r squared common from the denominator of here. So this i's will cancel, r squares will cancel, m will go to the numerator. So we have t equals to mg divided by I plus m r squared by I. So again you can see the tension in the string is mg divided by a term greater than unity, which means the tension in the string will be less than the net weight of the object. This is due to the inertia or moment of inertia of the solid cylinder.